Welcome back, everyone. Last week we talked a little bit about work and potential energy and kinetic energy. And this week I'm going to show you how we can use the concepts of energy and what we added this week of momentum to be able to solve problems um, about motion, but also about collisions. So, um, just as a way to recall, remember that the total energy of some closed system is always going to be conserved. When we're considering objects like projectiles, right, the energy considerations that we have to make are going to be the gravitational potential energy and then the kinetic energy. Because the total energy is conserved, right, the initial energy of the system should be equal to the final energy of the system, or the initial potential and kinetic energy should be equal to the final potential and kinetic energy when we add them up. And so here I just have the equation written out for you in terms of initial values and final values, but you'll see that you won't always need this whole equation to solve everything that we're going to talk about. Sometimes you'll just need part of it. So let's take a look at an example. A 5.6 kilogram stone is dropped from a height of 135 meters. What's the total energy of the system just before the stone is dropped? Well, we want to find then the initial energy, which in this case would be the initial gravitational potential energy plus the initial kinetic energy. Just before the stone is dropped, though, there is no kinetic energy. The stone's not moving. It only has potential energy. So this is zero. We can just eliminate this. All we need to know is the potential energy when it starts. And the gravitational potential energy is m times g times h. And I'm just going to put an I with that as the initial height. And so the mass is 5.6. G is 9.8. And then the height, 135 meters. For a total energy of the system, 7,408.8 joules, or essentially about 7.4 kilojoules if we divide by 1,000. So this is the total energy of the system. As that stone is falling, the energy can't go up or down. This total number has to stay the same. So as the stone falls, it'll increase in velocity and its kinetic energy will go up, but its height goes down, and so its potential energy will go down. So let's look at another point in the stone's fall. What's the potential energy when it is halfway through the stone's fall? Well, halfway, we're just going to write this as h of 1/2, is going to be the total height, 135, divided by 2, or 67.5 meters. To find the potential energy at that point, again, we're just going to have m times g times h. This time times the 1/2 value. I'm sorry, my pen's being a little strange. And so everything else is the same, 5.6, 9.8. But now we're going to use the height that it is at when it's halfway through its fall, right? Halfway as it's falling. So 67.5, 135 divided by 2. And all that really does is divide the total energy by 2. And you wind up with a potential energy of 3704.4 joules. So if the potential energy has gone down by essentially half, well, what happened to the kinetic energy? Right? As the stone falls, it speeds up, the kinetic energy goes up. Remember that the total energy of the system that we found at the beginning, this cannot change. That is going to be the total all the time. So if halfway through the fall, the potential energy is 3704.4, then the kinetic energy halfway through the fall has to be the total, or the initial energy, which was 7408.8 joules, minus the potential energy halfway down, 3704.4 joules, which, if you subtract the two, will give you 3704.4 joules. One of the reasons that energy is so useful in solving these types of problems is because some of it is kind of intuitive. Halfway through the stone's fall, the potential energy is half of what it was when it started, and the kinetic energy is half of the total energy, and the potential and the kinetic energies are equal. As the stone continues to fall, the kinetic energy will continue to increase, and the potential energy will continue to decrease. We can determine how fast the stone is traveling at this point by just using the fact that we know the kinetic energy is 3704.4 joules. We set that equal to 1/2 m times v squared. Okay, remember that m is 5.6, so we're going to divide both sides by 1/2 times 5.6. Okay, and then what we find, I'm just going to move over here, is that v squared is going to be equal to 3704.4 divided by 1/2 times 5.6, which will give you 1323. And so we take the square root to get the speed, and we find that v is equal to 36.37 meters per second. Now, without wasting your time 36.37 and showing you the calculation again, if you were to calculate this using the acceleration due to gravity and kinematics like we had done previously, you will get the exact same answer, and that's exactly what you should expect. Doesn't matter which way you solve the problem, you should always get the same answer because it's the same problem. And so we could do this using kinematics, or we could do this using energy. And sometimes using kinetic and potential energy is just easier. We lose information about which direction an object is traveling, but if we know something is falling, we already know which direction it's traveling. So to show you the usefulness of this, let's do the last part of this example. What's the speed of the stone just before it hits the ground? Well, we know that the total energy of the system, what we started with, 7408.8 joules. By the time just before it hits the ground, all of this potential energy has now become kinetic energy. Right? The height just, I'm sorry, I meant to write an F there. The height just before it hits the ground, right, is the height just before the ground, sorry, is equal to 0. And so there is no potential energy just before it hits the ground. It's all kinetic energy. All of the potential it had at the beginning is changed into kinetic just before it hits the ground. And so if we want to know the velocity or the speed just before it hits the ground, we just take the total energy and set it equal to 1/2 mv squared. I do want to point out one thing here. So I'm going to back this up real quick because we can solve it this way, but I want to show you something else that makes this a little bit easier. And something that will show you mathematically something you have been told a few times over the past few weeks. Remember that the initial energy has to be equal to the final energy. And so the initial potential energy, mg times the height, is going to be equal to 1/2 times mv squared. Now, if you are not extremely comfortable with algebra, that's okay. But trust me when I tell you that you can divide any equation by the same number on both sides, and it won't change anything about the equation. We can divide both sides by m. If the mass of the object remains constant, then the speed of the object just before it hits the ground doesn't depend on the mass, as we've talked about for a couple of weeks now, right? Based on Newton's laws. And when we were talking about objects falling last week, right? When you were dropping paper clips and coffee filters. If you made that mistake in your lab, I told you the mass doesn't matter. All that matters is the air resistance. Well, here I can show you mathematically that the mass doesn't matter, because we can just eliminate it from the equation entirely and calculate the velocity of the object without ever knowing the mass at all. And so if the equation or the question in your homework asks you to solve something, but they don't include the mass and you feel like it should be there, remember that you might not need it. And you might just be able to eliminate it. And so just be careful with that. And if you need help with this little algebra trick, please ask me questions and I will help. If we finish this, I'm just going to do that 1/2 v squared is equal to g times h. I'm just showing you a way to find v. If we multiply both sides by 2. Giving you a formula for the velocity of something falling like this. The velocity is going to be equal to the square root of 2 times g times h. And so if we want to know the velocity just before it hits the ground, when all of the potential energy has been converted into kinetic energy, then we just want to find the square root of 2 times 9.8. Sorry, 9.8 times 135, which is the square root of, which when you calculate it should give you 51 something. The velocity will equal 51.44 meters per second. Notice that it didn't gain as much speed in the second half of the trip as it did in the first half, because it's traveling faster and it covers that distance more quickly and doesn't have time to speed up as much. You could do this for any point in the rock's fall to calculate how fast it's falling, or what the speed is at that point. That was kind of a long, drawn-out example, but it's a bit of a classic example in understanding how potential energy and kinetic energy are related when an object is falling in free fall. Let's talk about a few other things that we can do with conservation of energy, and then we'll talk a bit about momentum. A ball is dropped from a height of 8 meters and loses 27% of its kinetic energy when it bounces on the ground. To what height does it then rise after the first bounce? And what about the second bounce? Now, this is a little different because we lose some kinetic energy to it bouncing, right? In a closed system like an object falling, there are no external forces beyond gravity, but that's part of the system, um, that are going to reduce the kinetic energy so long as we ignore air resistance. But when something bounces, when something comes in contact with the ground, right, or some other object, there's friction, and that friction generates heat, and heat causes you to lose kinetic energy. And so when a ball bounces off the ground, you'll notice that it won't, if you just drop it, it won't bounce as high as it initially did when you first dropped it. Right? And each successive bounce, it'll bounce a little, it won't bounce as high each time. It's lower and lower to the ground until eventually it just stops bouncing, right? All of the energy is lost in the bounce itself. We can use energy to figure out how much or how high something is going to bounce if we know how much energy is lost with each bounce. Okay. Now, I've meant to add the mass here, even though I told you guys it does not really matter. It doesn't, but it will make this a little bit easier for us to talk about. So let's say that this ball in question here is 0.35 kilograms. It's a relatively large ball, I guess. Dropped from a height of 8 meters, it loses 20% of its kinetic energy when it bounces on the ground. Okay, well, its kinetic energy when it bounces, right, just before it hits the ground, is the same as its potential energy right when it's dropped. And so its kinetic energy on the ground, I'm just going to put a little g there, 1/2. Well, let's not confuse that so much. Let's just say this. The initial energy is equal to the final energy. And that final energy is the kinetic energy at the bottom. And the initial energy is the potential energy, mgh. And so in this case, that would be 0.35 times 9.8 times 8 meters. And this gives us a total energy at the beginning, a total potential energy at the beginning of 27.44 joules. All of this potential energy becomes kinetic energy just before the bounce. During the bounce, it loses 27%. And so after the first bounce, right, the kinetic energy after one bounce is going to be 73% of 27.44. Right, the remaining 73%, or 27.44 times 0.73, which gives us 20.0312 joules. All of that kinetic energy that remains will be then converted into potential energy as it moves to the top of its bounce, right, as it bounces back up into the air. Because the mass and g don't change, we can calculate then the height of the bounce as the kinetic energy divided by m times g, right, or mgh, and then you just divide by m times g. So 20.03, 12 divided by 0.35 times 9.8. And the height after the first bounce is going to be 5.84 meters. This should make sense, right? It's not going to bounce higher than it did if it loses some of its energy. But it also shouldn't be really, really close to the ground either. And so look, we can talk then about the second bounce. And I'm just going to change to a slightly different color if it'll show up okay. And so the second bounce, we lose another 27%. And so now we take 20.0312 times 0.73. So I'm having issues writing threes with this pen today. And that leaves us with 14.6228 joules. So this is after the second bounce. And then if we divide by 0.35 times 9.8, we'll find that the height after the second bounce, 4.26 meters. And so you could continue this process until you got to the point where the ball stopped bouncing very high up off the ground. Right? Eventually, this 27% would change if this was real life. You're not going to do this exercise or this exact example, but you're going to do something similar in one of your upcoming labs, and that's the reason why I'm going to be sending you guys those poppers to use, is because you're going to be looking at how much kinetic energy is lost as it launches, as it bounces off the ground. If you've not filled out that form that I posted, now would be the time to do it because those things are going to go in the mail probably next week. So make sure that you're doing that. I'm going to pause here and break this video into two, and we'll pick up with the second half about momentum in the next video.